Hey everyone, let's jump right in. Today, we're stepping into the fascinating, behind-the-scenes world of the Airports Authority of India, or AAI. You know, airlines usually get all the glory, but AAI is really the invisible architect of our civil aviation infrastructure. They're the ones actually providing the air traffic management, running the radar installations, and keeping the communication systems alive across all the major air routes in Indian airspace. It's an absolutely massive, complex operation, and we're going to break it down in this explainer.
Seriously, think about this for a second. Have you ever wondered how literally thousands of flights share the sky at the exact same time without colliding? Just try to picture the sheer chaos of unmanaged airspace. With the crazy volume of modern air traffic and complex holding patterns, human eyes and basic radios just don't cut it anymore. What we actually need is a massive, interwoven technological safety net to keep everything running smoothly and, most importantly, safely.
And that brings us to the Air Traffic Services, or ATS complex, at the Kempegowda International Airport in Bangalore. Think of this as your behind-the-curtain tech tour of a real-world facility. We're going to be exploring this incredible world through the first-hand experience of an engineering intern who actually spent time in the communication, navigation, and surveillance wing right here inside this building.
All right, here is our flight path for today. First, automating air traffic control. Then, the aviation messaging network. Next up, radar, eyes in the sky. After that, precision navigational aids. And finally, VHF communications. Let's get into it.
Section 1. Automating Air Traffic Control, basically the brain of aviation. Because of intense traffic demand, controllers absolutely need automated help to organize the flow and prevent disasters. So let's decode some of this aviation alphabet soup, shall we? First, you've got the Flight Data Processing System, or FDPS, which handles your flight plan. But the safety nets are where the real magic happens. STCA predicts conflicts about 2 to 3 minutes out. MSWA warns of potential terrain impact. And MTCD provides conflict advisories up to 30 minutes in advance. Then you add an ADS-B to broadcast aircraft positions, CPDLC for digital messaging between the pilot and the controller, and DMAN to optimize runway throughput. These systems literally warn controllers to move aircraft away from danger way before human eyes would ever notice a problem.
Now, to handle that sheer scale of data, facilities use setups like the Celex automation system. It brilliantly logically partitions tasks into two main parts. You have the ATNS, which supports en route and approach control, and then the ASMGCS, which handles the tower control for all the surface movements. It basically takes all the incoming radar tracks, the flight plans, and multi-sensor data, formats the whole shebang, and feeds it directly to the controller's working position.
Moving right along to Section 2, the Aviation Messaging Network. This is the nervous system.
This nervous system runs on the AFNT, or Aeronautical Fixed Telecommunication Network. And a really crucial point here is that not all messages are created equal. Depending on the category, each message carries a specific priority indicator. Just look at the top tier, SS. This is strictly for distress messages reporting grave imminent danger, and it takes absolute precedence over everything else to ensure an immediate emergency response. Right below that, you have urgency messages, flight safety, meteorological forecasts, and finally routine administrative messages for facility operations.
To guarantee none of these vital messages are ever lost, the system uses what's called a store and forward principle. It's exactly what it sounds like. Data is transmitted, hits an automated switch, which is backed up by heavy-duty servers, RAID disks, and X25 routers, and it's temporarily stored there. The network analyzes the destination and then forwards it exactly when the path is clear. So your crucial flight safety data never just disappears into the void, even if the network gets busy.
But how does the network know exactly where to send it? Well, it uses a totally ingenious 8-letter addressee code system. It acts kind of like a highly specific postal code for the sky. The first 4 letters indicate the location. Take VOMM, for example. The V stands for the routing area. The O differentiates the state or region, which in this case is the southern part of India, and MM specifically identifies Chennai. It's a brilliant way to let a global system instantly route data right down to a local specific terminal.
All right, Section 3, Radar, the eyes in the sky. Radar stands for radio detection and ranging. And honestly, the physics involved are beautifully simple. The antenna transmits an electromagnetic wave out to a target and then receives the echo back. Because these waves travel at a constant known speed, the system just times how long that echo takes to return. Using a basic physics formula, it calculates the exact distance of the aircraft. It's pretty elegant when you think about it.
But there are actually 2 totally different types of radar working together out there. Primary radar bounces signals off a passive target. It's independent, sure,
but it requires massive amounts of power and has pretty poor efficiency. Secondary radar, or SSR, completely changes the game by requiring an active transponder on the plane. Through monopole secondary surveillance radar, the ground basically interrogates the aircraft. Via Mode A, it acts as an identification friend or foe system, sending a 4-digit ID code. And via Mode C, it reports exact altitude. So primary radar just sees a blip, but secondary radar actually asks the plane, who are you and exactly how high are you flying?
And this is what that looks like in the real world. This is the heavy-duty radar installation maintained by AIA at the ATS complex. It's a great reminder that all these abstract radio wave concepts and digital data networks actually rely on massive physical infrastructure out in the field. Infrastructure that needs constant, rigorous maintenance and calibration by skilled engineers to keep us all safe.
Which brings us to Section 4, Precision Navigational Aids, the guiding hands.
So radar helps the controllers see the plane, right? But what helps the plane see the runway? That brings us to navigation, officially defined as the art of determining an aircraft's position and guiding its progress from one place to another. While radar watches the plane from the ground, nav aids, like DVOR for azimuth guidance and DME for slant distance measurement, allow the aircraft to calculate its own exact position in the sky.
The absolute crown jewel of nav aids is the Instrument Landing System, or ILS. Think of it as creating a massive, invisible funnel in the sky. As a pilot approaches the runway, they pass over the outer and middle markers. These act as highly specific position fixes. They actually trigger lights and tones right there in the cockpit, working in tandem with the physical approach lighting system on the ground to confirm to the pilot that they are exactly, perfectly on path.
The ILS builds this funnel using two main components. First up is the localizer, which provides lateral guidance, basically acting as the left-to-right guide. It transmits overlapping frequency lobes straight down the runway centerline. By comparing the strength of these two signals, the aircraft's instruments can tell the pilot if they're drifting a little to the left or to the right, keeping them perfectly aligned with the exact center of the runway during descent.
Then, working right alongside the localizer, you have the glide path, or glide slope. This provides the vertical guidance. It projects a precise beam up into the sky, typically at a steady 3-degree descent angle. This is absolutely crucial because it ensures the aircraft doesn't come in too high, or worse, too low.
Depending on the accuracy of these signals, ILS approaches are broken down into different categories: Cat I, Cat 2, and Cat 3. These categories dictate the decision height and the required runway visual range, or RVR. This is a huge deal. With a high-end Cat 3 system, planes can be safely guided down to the tarmac, even when the visibility is so bad the pilot can barely see past the nose of their own aircraft due to dense fog.
And finally, Section 5, VHF Communications and Conclusion, the voice. Okay, we've covered the brain, the nervous system, the eyes, and the guiding hands. Now we arrive at the voice, very high-frequency communications. The civil aviation VHF band operates between 117.975 and 137 MHz. AII uses really advanced software-configurable hardware here, like the DTR-100 transceiver. Not only is it highly immune to interference, but it actually supports the military band and future VHF data links. You also have DATIS, a system that automatically decodes weather data into continuous voice broadcasts for pilots. And why does that matter? Because automating those weather broadcasts frees up the human controllers to focus strictly on their main job, separating traffic.
Everything we've covered in this explainer comes directly from a report by an engineering intern who got real, hands-on experience with these exact AI systems. As they noted, they acquired CNS familiarization along with a real focus on the vital role played by electronics in aviation. And honestly, bridging textbook engineering theory with these massive, physical, real-world systems is exactly what keeps the global aviation industry running safely and smoothly every single day.
So I'll leave you with this final thought. The next time you board a flight, buckle your seatbelt and look out the window. Will you think about the invisible web of automated data, global messages, radar beams, and radio waves that are constantly working to keep you safe? Seriously, if you look closely as you taxi down the runway, you just might spot the localizer antennas or the spinning radar arrays we talked about today. Thanks so much for joining me for this explainer, and keep looking up.